final topic in our coverage of operating system is called protection and security. So let's first define what we mean by protection and security. So we mean by security is preventing the access from external agents. So you can see that these things happen in terms of computer system as well as in terms of building or any other kind of like documents and etc. So and then we have like security means like this is security. It would block access or external agents to the system that we have here. And then we have protection, which means that we want to prevent the access of internal users from accessing resources that they are not allowed to. So in this case we have two users, for example, in our system. Like imagine that this is say that this is a guy that's not from Matthew, okay, and then this is say it's me, okay, and then this is another friend of yours, okay, whereas this guy is someone else. So this is the main difference between protection and security, that meaning that they are related, but they are different concepts in operating systems. So the goals of protection means that it stems from the multi-programming operating systems because we have a lot of users and they can share. We want to make sure they share common resources such as memory, files, and other things. And in the case of protection, we want to prevent violation of access restriction by a user and distinguish between an authorized and unauthorized usage. And we want to make sure that we provide a mechanism to enforce these policies of governing resources. And you can imagine that like some of these policies, they may be fixed during the design of the system. Some may be set by the management of the system, like the system administrators, and others may be defined by the users of the system. So the principle of protection is that it's the principle of least privilege. This means that programs, users, or systems, they should be given just enough privileges, okay, to perform their tasks. Okay, so when you're doing this, you have to ask, what's the lowest set of privileges allowable for this user to accomplish his task, and how long these privileges are required. For example, in the case of your US students, we want you to have access to the buildings, the campus, and so on. But we think about what's the lowest set of privileges. For example, you may need access to the say so to the labs and to the canteen, to the say bathroom, to the toilets, and to the common basically areas. But you should not have access to, for example, to the room where we have the system servers, or to the photocopy room where we may be photocopying exams and so on. And we have to make sure that how long do we have these privileges need to be used for you. For example, in our department, yes, we were providing 24-hour access, but in other departments, you can imagine that after regular working hours, the buildings may be closed because they were not required. So in this principle of least privilege, for example, if you hire a gardener to handle the gardening in your garden, then you want to grant them access to your yard, but not to your bedroom. Okay, so the fact that you're hiring him, that doesn't mean that he has access to everything. Or you want to grant them access, say during the afternoon when they are working, but not at midnight. Okay, so that's the idea. Now, the second concept is the domain of protection. So the operating system, it consists of a collection of objects. So this can be hardware or software. For example, files, directories, say hardware. These are all different objects, and they have basically, for example, we can have a file that can be readable but not writable. Okay, and we assume that each object has a unique name that can be accessed through a well-defined set of operations. For example, a CPU, this is an object that can only be executed on a memory can be read or written, and we can even try them, like some portion of memory can only be read only or execute only, or others can be read but not written, etc. Or the CD-ROM can only be read. So we have this protection problem, which means that each object is accessed correctly and only by those processors that are allowed to do so. So how do we define a domain? So a protection domain, it specifies the resources that the process may access. So it defines a set of objects and the types of operations that can be invoked on each object. So here we have a domain. So it's basically a set of access rights, and where each access right can be used as a tuple, like here's the object name and here's the right. And the right can be, for example, read, write, execute, whatever those types of accesses. Okay, so here we have, for example, we can have like different domains. Let's say I have a process that's P1 and P2. They are running in different domains, and say that P1 is running in domain 1, and when it's running in this domain, the file A can be accessed by read, write, and execute. The file B can be read and executed. Page 2, like in the memory, it can be read, or printer 1 can be printed. Okay, whereas P2, it's running in a different domain where file A can be read and written, but not executed. Okay, and file B is as such. Page 1 can be read and executed. Okay, and say printer 1 can be used to print. Now note that these domains need not be disjoint, and for example, both P1 and P2 processes, they can print on printer 1, okay, but only P1 can execute a file A, and only P2 can read page 1. So this domain structure, it can be static or dynamic, and the associations between a process and a domain can be static, meaning that when you create the process, then its domain is already set and it's fixed, and it means that so it may need to provide more rights than needed at the runtime. Or we can look at, for example, like this in the case of a static, you can imagine that, say I'm running this PowerPoint, and say if it has the possibility to print, then should I allow him to print? Okay, maybe like 99% of the time it won't use it. So if it's a static association, then I'm not caring about the runtime. Basically this is a static case. In the dynamic case, a process can switch from one domain to another one, and the content of the domain can also be changed. So here we have an example of P1, that is basically file A, read, write, execute, and printer 1 and print. Okay, and we can, in the dynamic case, we can make the P1 can switch to one domain to another one, say to domain 2, and now it has different accesses in here. Or, like in time, the content of the domain can also be modified. So how do we define this domain? Well, each user may be a domain, and these access rights can then depend on the identity of the users. Okay, and domain switching occurs when the user is changed. You can imagine that this is, for example, happening at the file system. When you're as a user and you log in, then the access rights to your files are depending on who you are. Okay, and each process can be a domain, meaning that the access rights can depend on the identity of the process. And the domain switching means that, one process may be sending a message to another one and then waiting for a response. Or it can be a procedure. Each procedure may be a domain. Okay, and this is what we mean by this is that it's a set of objects that can be accessed by it corresponds to the local variables defined within that. And this domain switching occurs when a procedure call is made. And for example, when you make a system call, this is a case where we have a domain switching, okay, which means that we switch from the user domain to the kernel domain, okay, and the process that run is in kernel mode and they have the right to execute privileged instructions, but at the same time we also need to protect users from each other. So in the Unix world, the domain, each domain is associated with the user through the user ID and the group ID. Okay, and switching domains means changing the user identification temporarily. And the switch is accomplished by the file system, and where we have each file is associated with an owner domain and also an owner identification and also a domain bit, which is known as the setuid bit. So at this time, let's talk about this interesting thing that how does the password program work, right? Now you can imagine that there's a file that's called etc password. Okay, you may have already discovered this, and in this basically file, then you have it's a file that contains the encrypted versions also. So this is our password file, and it says that here is my Ali, and then here's the encrypted version of the password. Okay, 1C5 blah blah etc. There is some string here. This is the encrypted copy of your password, and then here we have Willy, and it has something else, and etc. So in this, when you enter your password, and if your name is say Ali, then your password, whatever you entered, it's encrypted, and it's compared against this encrypted copy in this etc password file. And if it's the same, then you're granted access, otherwise you're not. Okay, that said, you can imagine that now this file, if I want to access this file, you say using your editor, so vi, etc, and password, well, can you change it? Well, no, this you cannot access it because if you can access this, then you would be changing anything here, right? So that's not feasible. But now, as a user, now here you run vi and you cannot modify etc password. But if I do, if I say password command, okay, which takes this etc password model with this password, now you can change this file, okay. Now, you can imagine this is very interesting because, VI was running as me, right? So this is a process that's running with my credentials, and it doesn't have any credentials to update the password file. And then I run password. This is an executable, just like a VI executable. But now this password file, when I run this, then I can change the same file. So how does it happen? I'm if vi cannot update it, the password file, but this password command can update the same file. Okay. So this is an interesting case where we have is in the password program, the way it works is that if we have a user, okay, with a certain A, and it's executing a file that's owned by B. Okay, when the setuid bit is off 0, then the user ID of the process is set to A. If the setuid bit is on, then the user ID of the process is set to B. So in this particular case, let's look at here. So I have these two executables, vi and password. Okay, so with vi, and here's the password. Okay, and the setuid bit, and I'll show you how it. In the setuid bit for vi, it's set to 0. Setuid bit. Okay, in the password, it's set to 1. Okay, and vi executable, now its owner is, well, it's root. Okay, and this one password, it's also root because it's a system executable. So these files are owned by the root. Okay, now what we are saying is when the setuid bit is 0, and when I run this executable vi, now it would run as me, as Errol. Okay, so it would run within my domain. But if the setuid bit is on, or it's 1, it means that it would, if I run password, then it would run as the root. Okay, this is a crucial thing, and as a result, it can then modify the password file, which is here. Okay, so this is something that's basically it takes it sounds a little bit complicated, but I want you to think about this, basically how this actually works. Let's see how we can model protection. The easiest way to model protection is in terms of an access matrix. Okay, so in this case we have the rows which represent the domains. So here we have domain 1, 2, 3 to 5. Okay, and we have then objects which are represented as the columns. And in each intersection, in each cell, then we have the XSIJ, which is the set of operations that a process executing in ith domain can invoke on object J. For example, in this particular case, if we have a process that's operating in domain 1, it is marked as the owner of object 1, and it can read, write, and execute. And on object 2 it can just read, on object 3 it can just access, and here we have another object, so another process that's working in domain 2. It can read and execute on O1, but it also has the ability to switch to D1. We'll see more about these. So for the access matrix, we will have some dynamic protection. It can be that means that we have operations to add, delete, or these access rights. Okay, there are some special access rights, such as being the owner of an object, or being able to copy an operation from an object I to an object J, or control, which means that a DI, a domain I, can modify DJ's access rights, or switch, which means switching from one domain, from the ith domain to the jth domain. Now, we can see this in an example in the UNIX world. Again, this is the ls-l of a directory and the content of the group, which is shown here. So in this particular case, this is how we have files. So as objects, we have these files: useforce, 3po.man, ds.plan, mf.jpg, and then we have these owners: ob, luke, dart, and han, which belong to different groups. For example, ob and luke, they belong to the Jedi group. Dart is a member of Sith group, and han is free. And then here we have these protection bits, and in the protection bits you can see that the first one declares whether it's a directory or a file, and then here we have the user's read, write, access. Okay, we know these. And in this particular case you can see that we also have this S, which is the setuid bit. So this is a file that for this useforce, its setuid bit is set to 1. Okay, and in the etc group, this is where we have the lists of groups. So we have the Jedi group, Sith group, free group, and robot group. And so like in this case, like the second item is the shadow password, meaning that the passwords are basically stored in a shadow file, which we'll be discussing later. And in the Jedi group we have Yoda, Obi, and Luke, and in the Sith we have the Emperor, Vader, and Dooku. Free is Han, Leia, Obi, Luke, and in the robot group we have R2, D2, and 3PO. And so based on this, we have the following access matrix. So for example, useforce, and this is the domain, this is the object. For useforce, it's the owner, it can read, write, and execute. For 3po.man, now it has the ability for Obi, it can read it, okay, because it's readable by the group. You can see that it's this 3po.man. This file is readable by the group, okay, and that's why you can read it. and there's the DS plan. It can access DS plan. You can see that here's the object, and we can access, meaning that this execute access that is available to group and others. So that's why it's accessible. And let's see that, for example, for look, we have the read and execute on the use force. On the use force, we have read execute because for look it's a JEDI. So this use force file, this is owned by OBI, but at the group level, which is the JEDI level, all JEDIs can read and execute, and Luke is a JEDI, hence he can do that. Okay, and whereas for 3po.man, and he's the owner, and etc. Okay, so you can study this access matrix, and it will be a really good idea to study of basically these UNIX versions map onto access matrix. Now we can switch between domains, and which means that like along with the domain, here's my domain, here's the object, say different files, and we can also have these different domains listed here, D1, D2, D3, D4. So the fact that I have a switch access here means that D1 can switch to D2 domain. Okay, and this is, and for example, so a process that's running in D2 can switch to domain to in D3 or D4. Okay, and in the Linux case, the sudo implements this domain switch control as listed in etc. sudoers, and this basically allows the control change of the contents of the access matrix entries. And now, in order to do this, we need to have support 3 additional operations, which is copy, owner, and control. So let's discuss this next. So the first one is the copyright. So in this case, copy means the ability to copy and access right from one domain, okay, to another one. For example, in this particular case, we denote the copyright for an access right with star. So let's say it, for example, for a process that's running in domain 2, it has read access to file 2, okay, but it also has this star. Now, star means that this read access can also be copied to someone else. Okay, then you can see in here that since it has this star, which is, then it means that it can copy this to here as shown in here. Okay, so this is the right to copy, and here we have this example that in SQL, for example, when you SQL grant with grant option, then it allows you to do so. Now note that when we do copy, there are 2 possible variants. Okay, the first one is when you write is copied from ij to ki, then it's removed from ij. Okay, what this means is this is more like as such. So here we have this, let's say that here's our domains. Okay, in this particular case, if I am if I have, say, if I have this, okay, and if I copy this, right, so this is my di, this is dj, okay, if I copy this here, and after this copying operation, like this, okay, so initially, let's, okay, so let's try this. So in this particular case, initially, so here's I say F2, and here's D1 and D2. Let's say that I have R access. Okay, in the first version, which is marked here, and in this case, when you do so, you can, after this you have F2. After copying this R to D2, now you lose the write to F2. So now this will has read. Okay, this is the what I mean by this. And the second thing is the propagation of the copy, which means that this in the second version we have, again, let me see, F2, D1 and D2, and what you do is you can copy. After the copy you will have F2 here, D1, D2. Now this will have as such, and this will have the read. Okay, now in this case it's not R star. Okay, it is R, meaning that D2, anything that's operating in D2 that can read, but D2 cannot, for example, give D3 the access right to read it. Okay, so these are the two possible variants of the copyrights. And we give you, like in this particular case, let me show you why, for example, something like this is important. This one is, for example, it's interesting because in Windows, in some versions of Windows, for example, you can imagine that this is a user, okay, say, and if let me see that if the root wants to access a file that's owned by the user, okay, say that this is the user and D2 is the root, okay. Now it can forcibly, for example, copy this to himself, but upon copying, have this reading right, then the user loses access to that file, and which means that the root can actually change or access the files of the user, but when the user comes back, he will note that the root has changed it, because after doing this it cannot give it back to the user. And the second one was owner rights. Now owner rights, basically it's the owner basically it should allow the addition of new rights and removal of some rights, and this is basically implemented by chmod. And here we have, for example, in this particular case, D1 is the owner of F2, meaning that when it can execute, so by doing this it can remove the access to this file in D3 because it's the owner. Okay, so it's done. Or here we have, like in the case of D2, now it's the owner, so it can change it. It can say that I'm going to also have the right, and I will also give the right access to D3 because it's the owner. And the third one was the control rights, which is as I discussed before, if you're operating in D1, then you may have the right to switch to another domain if you have an access right here. So in this particular case, for example, D2, okay, it can along with switching, it also has the ability to control. It can modify the for role, okay, and what this means is D2, okay, can grant access for D4. So it can say this for if you are a process in D2, okay, then you can modify these rows in here, okay. And for example, in UNIX, the root has control right on all other domains, meaning that it can change the owner or the abilities of any other rows in here. And along with this, the copy and owner rights provide us with a mechanism to limit the propagation of access right. Okay. However, note that when we say, for example, when you share information, the fact that I am, for example, I'm giving somebody a read access, and for example, let me see here. So in this case, for example, D1 can read F1, right? And what if I give like a sense, let's say that this is an owner. So if this is an owner, now it can, and that this has this read star, because it can also grant others read access. So it can, for example, give D3 read access. Okay, but this has only read access, not read star, because it means that D3 cannot give, say, read access to D4. Okay, but what it can, like this is as said, so that it can read it, it can create another file that contains the same contents, and then allow D4, it will create another file. Let's call that's F5, and then it can grant it to read. So what this means is this following, that by making sure that we have these rights, you can see that they do not give us the appropriate tools for preventing the propagation or disclosure of information. Okay. The problem of guaranteeing that no information initially held in an object can migrate outside its execution environment, this is called the confinement problem, and this basically this is a very serious security problem. Now, for us in the operating system, all we have discussed so far, this applies to anything like building, documents, in military, and etc. Now, in terms of operating system, we need to discuss how we can implement this access matrix. And we want to do this in an effective way, of course. Now, note that the matrix will be sparse, meaning that we have a lot of domains. We have maybe tens of thousands, 100,000, or million objects just in the file system as well. Okay. Now, how can we, and we can also note that most of these entries will be empty. And there are different ways to implement this, and we will be discussing 4 different implementations. One is the global table, the other one is access lists for objects, third one is capability lists for domains, and the lock key mechanism. So in the case of a global table, then we can see that like for each domain and object, we can have these right set triples. So here's the domain one, for object one, these are the access rights. So we can have a global table that stores this. Okay. Now this is of course the simplest implementation, but the table is really large, so we cannot actually keep this in the memory. And moreover, it doesn't take into account special groupings of objects or domains. For example, if everyone can read a particular object, then it must have a separate entry in every domain. For example, you can imagine our, for example, shell executable, and I want it to be accessible by all the users, but for this I need to have an entry for, like in my entry that, let's say this is a shell, okay? So for all domains, D1, D2 to the N, then I should have grant this access, read, execute, and so on. So I need to have, for all domains, a copy of this. And more, I do not have, like, having these special groupings at the user level. For example, for students, or I want to share something with among the staff or faculty in our department. So it doesn't take into account all those special groupings, and it's a simple implementation, but it's really huge. Now, within this, we will see that, like, we can like this is, if this is a whole object, now we can, instead of this, we can split, like having this whole matrix, we can split it into 2 parts. The first thing is, for each we can have an access list for objects. Okay, this is the first particular object in domain 1, then I have read, write, etc. This is the access right. In domain 2 I have this. Okay, and for object 2, then these are the rest. So this is the access list for objects. Now let me go back in here. In this particular case, you can imagine that, like, in this case, you just group everything by the objects for a given object. Okay, this is the handle, this is the index that you do, then you lump your D1, like the domains and the objects as well. Okay, so here is, like in this particular case, can imagine that I have these files, okay, and for each file and for each domain, in this case I have like domains like A, B, and C, okay, as defined in here, and I have basically different objects which are as files F1, F2, F3, and different rights. So in this case, the access list is in, if you're operating in A, you can read or write, okay. If you are operating in B, then you can switch to A and then do so, and etc. So in this F2, it's readable in domain A, readable and writable in domain B, and readable in domain C, and so on. Okay, so this is basically how it works. We can do the grouping on the other side, which means we can have a capability list for domains. In this case, we lump them together by the domain. So when we define a domain, we say in this domain 1, object 1 has these rights, object 2 has these rights, and so on. Okay, so this is this capability list associated with a domain, but it is never directly accessible to a process executing in that domain. Rather, the capability itself is a protected object and maintained by the operating system and accessed by the user indirectly. So here's the same example in this particular case. Note that I'm grouping at the level of the domain, and this is my capability lists, meaning that if I'm in domain A, then I have the capability to read F1 to read F2. If you're operating in domain B, then you have the capability of reading F1, but reading, writing F2, and so on, and etc. Now, the last mechanism that we'll discuss is the lock key mechanism, and this is a compromise between access lists and capability lists. In this particular implementation, each object has a list of unique bit patterns called locks. This is, you can imagine, this is like the actual locks in our doors, okay? And similarly, each domain has a unique bit of patterns called keys. And when we have a process executing in a domain, it can access a domain only if that domain has a key that matches one of the locks of the object. So let me draw this. So for example, let's say that if we have a key, let's draw a key in here, okay, you can see that these keys have patterns like this, okay. Okay, so this is a key that I have here, and what we will do is the locks that I have here is maybe like the locks, okay. Okay, maybe this is my lock, okay. So this is the lock. Now, originally, you know that when this key, the patterns here match the lock here. So this is my lock, and this is the key. So you do this, you look at this matching, and you can imagine, for example, in our department, for example, I have what's called I have a key, and my key the key that I have, let's call this key E. Now this opens up my own room. So if I have this room, okay, this opens up my own room, okay. But the same key also has a certain what I want is I don't want any other faculty to be opening up my own room. So if I have if I have a different faculty, this thing, it should not be allowed. But I also want that, for example, we have some say the post the photocopy room in our department. Let's call this the photocopy room. Okay. In this case, I want both KE and KF. Okay. They should be able to access this at the same time. Okay, typically it's done by keeping something called some bit here, and that it basically unlocks. So this part in here, so let me see. So this portion of it's different for all the keys, but for all the faculty, they all have this single bit in here. Okay, and in the photocopy room, then it just checks this particular bit, and it's basically doesn't care what the values, what the parts in the previous key what the dents in the previous part of the key are. Okay, so as a result, using one key, I have the ability to open my own room. Okay, but all the other people, like other faculty, they can also, like, we can all use have access to the photocopy room. Now, in this particular case, of course, the list of keys for a domain must be managed by the operating system on behalf of that domain, and that the users are not allowed to examine or modify the list of keys or locks directly. So, meaning that this is a privileged instruction. So, if you compare these access lists, capability lists, and lock key mechanisms, well, access lists, they correspond directly to the needs of the users. So when a user creates an object, then she can specify which domains can access the object, as well as the operations allowed. But the capability lists, they do not correspond to the needs of the users. They are useful, however, for localizing information for a given process. So the process attempting access must present a capability for that access. And the lock key mechanism is a compromise between these two. So it can be both effective and flexible depending on the length of the keys, and the keys can be passed freely from domain to domain. So now let's move on to a couple of other things to finish the whole discussion. So first, authentication. This is a crucial part of the security, and it's if this request is really done, like if somebody wants to log in, then we want to make sure that it's the actually that user that it claims. Okay, and usually host authentication relates to network request, and this is outside our course. But the user authentication, well, this is something that is done when a user, say, logs in, starts a session, or asks for a privilege operation. So usually, like, this is again, like, this is an issue that we are discussing in the context of operating systems, but it's also valid for buildings, for documents, anything that you can have. Okay, so the authentication is done usually by something that only you know, like a password, a PIN code, yours, like the TC kimlik number, etc. Something that you have, only you have, like an ID card, credit card, cell phone, smart card, or something that you are, like your finger, maybe retina, blood, DNA, etc. Okay. So, in one of the most common ways to authenticate is the use of a password. Now, this means that there's a passphrase that's known only by the user, and this user password is compared against the information stored on the system, and if there's a match, then there's a success. And so this password is a critical part, and protecting password database is very crucial. Now, it's a bad idea to store these passwords in plain, meaning that as text, because if somehow somebody gets holds of this password file, then the whole security of the system collapses. Okay, and moreover, like the privileged users can see the content and use it for other systems. For example, the root. You may be using the same password on another system, so we don't want the root to see your password in plain text, right? So the solution is to use cryptography, and the idea is we use hash or digest function to map a string of bytes, okay, onto a fixed string. So that means that given the string of bytes, the original string cannot be computed. Okay, so then a small change in the input string ends up an extensive change in the result, and there's no correlation between them, and then having two input strings results in the same value is extremely unlikely. So typically the user passwords are stored in database as a crypto hashed values. Okay, and in this particular case, with the function, the authentication is as such. So we input the username and the plain password from the user. Then we pass this with this crypto hash function, this string, and we get a CPass. This is like a basically a crypto string. And then we check this password database for an entry with the username as such and the CPass as such. Okay, and so and then there is no, like in this particular case, like it's in this POSIX case, you can have this crypt key and salt for functions for password test. Okay, you can do that, etc. And usually the etc. shadow is used as a password store in standalone Unix Linux system. It's not a perfect solution, but it's vulnerable to dictionary attacks. What it means is, like from the dictionary, like most people may use some common strings from dictionary, and you can pass all these, like these strings. So since this whole crypto hash function is available, then you can pass all these strings into them, and if they match any entry in this in this shadow file, then bingo, you get the key. Okay, and of course, like there are other things like social engineering attacks, meaning that you can learn from user it's his birthday, then he's supporting, etc., etc., his father's name, his I don't know, like his girlfriend's name, and use them to generate some possible passwords and try them. And of course, like key loggers and etc. There's this doesn't tackle that. So the major problem in password authentication is its lifetime. So a user may be using the same password for a year, and so that means that we need to have some frequent changes to password or PIN code. Now, the one-time password or OTP, it uses cryptography to generate dynamic passwords as users' authentication over time. So in the case of a sequence-based, we can have, like, there's a certain sequence, and given the previous one-time password, you can generate a new one-time password. Okay, or if it's time-based, then you can have again use the time of the day and then generate it again a new one. And the user cannot compute the OTP gen, so either it's pre-computed or he's given a device, like it can be your, for example, your cell phone, an app on your cell phone, and it can generate OTPs as needed. Okay, so this OTPs then turns this authentication problem into something you have factor authentication. And there's also the third-party authentication, as implementing a password or OTP based authentication is complicated. Like sometimes you have to use some centralized basically server to do this. So the user asking for the authentication is then sent to authentication services on the network. The user authenticates him in the server, gets a ticket, and then the ticket is given back to the original system to finish the authentication. And cryptography basically makes sure that the ticket is coming from the trusted service. And these things are like, there are these protocols on services like Kerberos, OpenID, and OAuth. And of course, there are like multi-factor authentications, and in high security systems such as your bank account, etc., it requires at least 2 factors in authentication, typically, for example, a password or a mobile SMS, or credit card plus PIN code, retina scan plus ID card, etc. Or sometimes, something that you have, like it can be fingerprint scanners, retina scanners, etc. And of course, like there are other uses of cryptography in operating systems. They can use them to check the integrity of the data. If a file, for example, a system binder has changed in the system, like such as a virus, then you can check this by computing this. This is what you do: is you have this crypto hash function. You pass the whole system binary through that, and you get a value, and you store it in somewhere safe. And the next day you come back and you check it again. If it doesn't match, it means that someone must have tampered with the original file. And this is also done with the software package authentication. When you download a software package, you want to make sure that it's the original one. And there is the symmetric cryptography, okay, which basically in data privacy or encrypted content of the disk and file messages. And there's also the public key cryptography, which is used when you're sending basically secure emails, for example, to each other, where it ensures that there's the integrity of the data. The message that you send is verified. It has to be authenticated and encrypted, and the key exchange is done in a proper way.